Good afternoon, everyone. And it's a pleasure to be talking about Fourier transforms. I have sort of done a small, brief recap here of what we talked in the first lecture. Many of you must have already read this, but I will just go through it very quickly. So we looked at the basic idea of the Fourier transforms, underlined or emphasized its linear nature, its uniqueness, and this is possible due to the basis functions which are mutually exclusive and collectively exhaustive, which in this particular case of Fourier transforms, the basis functions are sinusoids. And we looked at several properties and saw examples relating to how the transforms turn out to be specific ones in the case of odd and even functions, how the linear combinations translate through the Fourier transform, how the scaling translates. We looked at some of the operations on the functions and how they translate into the Fourier domain, namely the correlation, convolution, modulation. And we also appreciated the Rayleigh theorem, also known as Parseval's theorem in the discrete domain, where the statement of energy conservation is stressed. So this is just to flash to remind you of the basic continuous transform, that continuous integral. Defining the transform is the way it's given. And one of the things I will keep coming back to and emphasizing is the conjugate variable relationship, which if there is a certain scale or width of the function in a given parameter space, you will find it's in its Fourier domain, the inverse coordinate will have width, which is inverse of the width in the one domain. So that is something that we will elaborate on in the context of coherence later. And we'll also be using that routinely. Among the various theorems and properties that I listed last time, the one I want to pick up today specifically is the Shift Theorem, which is essentially saying that if small f of x has a Fourier transform capital F of s, then a shifted version of the f of x shifted by an amount a, which can be written as f of x minus a, has the same Fourier transform in terms of its amplitude, but acquires an additional linear phase gradient, which is linearly proportional to the amount of shift, and the phase goes linearly across the coordinate s. So this example we had seen, and I'm going to revisit that. So a positive shift, which is nothing but a delay, okay? A positive shift defined as x minus x naught, let's say, as so where the original function, the function's original origin now appears at x is equal to x naught. So that's a delayed function, and delay causes negative phase gradient. So the phase term will look like this: exponential of minus I times 2 pi x naught times s. And it can be pictorially depicted as shown here in this middle sketch, where the phase will ramp linearly as a function of s. We saw the implication of it in terms of how the real and imaginary parts look like for what was an original sinc function with imaginary part 0, when the function was centered at 0, when it was shifted by an amount. You will find that the same amplitude and new phase now translate into a non-zero imaginary part as well. So, and the description is more explicitly given in terms of the component of the real part and imaginary part. This, of course, times the amplitude of the original function and whatever other phase it might have. So using this now, we are going to just take some of the functions and their transforms as the given. For example, the Gaussian translates into another Gaussian of the inverse width in the Fourier domain. We have seen over and over again that a box function, a rectangular window function, translates into a sinc function in the other domain. We have also seen that a delta function in one domain translates into a function which is constant as a function of the other coordinate in the frequency domain, or a function like this, which is constant across the given domain, translates into a delta function at origin. So now we're going to use this and see, and using the shift theorem, whether we can begin to understand even the transforms shown here. For example, here there is a cosine function, and you can see that you can achieve that by shifting this delta function on either side of the origin, which will translate to phases depending on the shift. In this particular case, the shift is in this domain. So it's a shift of S0, let's say, on either side. And it will translate to a phase gradient in the time domain, translating it into real and imaginary parts. And you can, using your simple maths, you can show that by putting these on either side of it, where the phase gradient is opposite of each other, corresponding to each one of them, the imaginary term will cancel out, and what we will have is twice the cosine term. And so that's what will give rise to a cosine function, which now we can relate in terms of a transform pair. So cosine function has a transform of two delta functions separated by an amount which is corresponding to the frequency of the sinusoid or cosinusoid. Similarly, you can have a phase shift of pi or two delta functions with opposite signs, and that will translate into similar expressions, except appropriate sign changes taken into account, in which case you will find the cosine term will cancel and you will have twice I times sine of the argument. And so that's a sine wave whose transform is two delta functions with opposite signs. So the same thing is given here. You have to take care of this factor I, the square root of -1, depending on where you put it. Be free of it in the other domain. You can also see that using one of the other theorems, which is autocorrelation function is a modulus square of has a Fourier transform, which is modulus square of the original transform. You can see that the triangular function can be achieved by autocorrelating a window function and of appropriate width. And so when you do that, you will find you get modulus square of this function in the transform, and which is now the sinc square instead of sinc. So you will find that with few building blocks, you can begin to visualize what the transform of other variety of functions would be. We're going to just play that game a little bit more. So you will find that if you're given two boxes like this, two rectangular windows like this, you can imagine this in a variety of ways. You can imagine that to be a window function of this width minus a window function of that width, of a narrower width. And by using linear superposition, you can write the transforms for both of them, which are sinc functions of different widths. And you will find that this function, the function with wider width rectangle, will have a narrower sinc function and a taller sinc function because of the area involved. And the narrower rectangular window will have broader sinc function. And so you will find of a slightly lesser amplitude. And so when you subtract the two, you will find net positive excursion at 0. But then because of the width of the narrow rectangular windows Fourier transform, which is wider, subtracted from it, you will see negative going excursions. When you take modulus square of it, this is what you will get. Regardless of the sign of the excursion, you will get a lobe which is on the positive side. This is just another variety of that. What is subtracted is, in this particular case, a smaller height window, and so you will find the negative excursions are correspondingly lower. You could also realize this in terms of two delta functions convolved with a rectangular window of this width, of narrow width here, which is the width of individual boxes here. And then you will find that it can be realized as, since it is a convolution of one function which has got two delta functions and one which is the rectangular box like this, you will find it will be product of the Fourier transforms of the individual functions. One of them is a cosine function and one of them is a sinc function. So you will find a cosine function multiplied by a sinc function, and this is what it will result in. What is shown here is the the picture within the first lobe of the sinc function. You can also see that if the separation is larger than the box width, you will get many sinusoidal ripples within the envelope that is created by the sinc. This is, of course, the function that we are using, sinc function, which is straightforward. You can also have a Gaussian, which is truncated at the ends like this, which can be realized as the Gaussian multiplied by a rectangular function. And the multiplication here in one domain should correspond to a convolution in another domain of the transforms. And so it will amount to a Gaussian being convolved with a sinc function. Now, one of the things while we are here, let me emphasize on something that I found fascinating in my early days when I was thinking about Fourier transforms. That the convolution is a smoothing function, for example. And if indeed this is an aperture distribution, then you know that this will be the corresponding diffraction pattern associated with that aperture. And when we take actual measurements, the data could extend beyond this where the noise contribution would be there. Even if you conduct multiple convolutions of the data in this domain by the sinc function, which has got, let's say, width no shorter than this extent, then you can show that you have not really spoiled any information. And that can be appreciated from this domain where successive multiplications of a rectangular window doesn't change the information. So you can achieve smoothing of the data without spoiling your original information, which is contained in the where the sky contribution is restricted to this window. This is something that you might use in practice many times. If you want to use a smoothing function, you will find the safest bet is to use a conservative rectangular function in the filtering domain, such a way that it corresponds to a sinc function, which you can use for smoothing, which amounts to where the information domain in the other, its Fourier counterpart, is not spoiled at all because it's multiplied by unity in the region of interest and it's the most multiplied by zero in the regions of where you're not interested. This we already saw. We can achieve without going through elaborate integrals, visualize triangular functions Fourier transform as sinc square. And this is the Gaussian. Sorry for some of the repetition, but I wanted to take some of these examples from the top in this diagram. So we're going to visit convolution, cross correlation, autocorrelation in great detail today. Let's see how far we get there. This is sort of a Wikipedia example of processes involved. If these are two functions, as traditionally described, you take this function, shift it, flip it, and then multiply. And so that's what is shown here. The flipped and differently shifted versions are overlaid on each other. And the product is computed, and the net result is shown in the thick black line here. And so a rectangular window with this ramp function here, triangular ramp, is shown here, where the convolution has a shape like this, which is achieved or which is a result of these successive operations as shown here. You can go through them elaborately. I will not describe them in great detail. You will find that when there is a complete overlap, which is at the center, you have the maximum overlapping area, and that's what leads to the peak. Cross correlation, on the other hand, is there is no flip. There is simple sliding of one function on the other, and you are trying to look for similarity between them, or at least some measure of similarity. So in this particular case, the maximum overlap occurs again at the same point. But the way the overlap increases is exactly opposite in direction of the convolution function. And you can appreciate what that means. Although mathematically these expressions might look similar and just flip of sign of one of the arguments, they are fundamentally very different processes. And that's what I would like you to appreciate. Autocorrelation is, of course, the same function cross-correlated with itself. And so that is shown separately for F and G, one below the other. You can see that the rectangular window turned into triangular window. This function turned into a sort of nonlinear function here. So these are examples that you can try and go through. There are any number of them. You can choose your picks on what it is. So this traditional way convolution has been described in the book and by most people as well is this stuff that I was mentioning, where you have these two functions g1 and g2. You flip the function, one of them, and then slide it over the other, and then as a function of the relative shifts, you will find out product and integrate it over the entire space. That is written as an answer. And the answers are shown here, respective things. But this is to me, I personally find it as a very convoluted way of thinking. It loses the physical meaning of the convolution, is lost in just this mathematical operation, which one wonders why one has to do this. So there is another better way, which is inspired by physical devices, where convolution happens routinely and naturally and implicitly. This is in almost all the physical devices, linear devices. All linear systems perform convolution implicitly and naturally. And so let's see what that means. What we have is a convolution. These systems perform convolution by their impulse response, okay? And that decides what we get at the output. So input might be one signal. Impulse response is another function, which is a description of the system. It does not depend on the input. It is regardless of the input. Its property is constant. Its Fourier transform, impulse response's Fourier transform can be described as its spectral response or characteristic function or transfer function. There are different names to it, which is basically the description of the same thing in the Fourier domain, corresponding Fourier domain. So this is what happens if you're looking for some pattern in the signal, and if you want to check a similarity of the pattern with some known pattern, then we can also use this physical device, except it cannot do the correlation. Correlation is not the natural operation. Convolution is the natural operation. But we can trick that into performing correlation, as we will see. So this is one example. Please don't get confused by a description here, which might appear like in terms of some electrical system. This is regardless of what the system nature is. We have some input and the system responds to it and gives out an output. The system response, as I said, does not depend on the input. The output depends on the input and the system response. And this is the hallmark of all the linear systems. So for every impulse, we are going to get this response. Let's say this is just an example of it. Let's say if we give an impulse, this is what the system responds with, a damped oscillatory signal. It might have a response time of which is corresponding to the inverse of the width of the Fourier description of this impulse response. And so all that is good. We're still following the standard conjugate relationship and so on and so forth. Now, there is no particular importance to a particular response I have drawn here. Could be anything that you can choose, except now we're going to use this to see how to describe the output. Now we can see that each input impulse at various times will prompt a respectively scaled and time shifted impulse response, and which when we superpose, it will provide a description of a combined response, which is the output, and which is indeed a convolution of the impulse response with the input train of impulses. And so we can simplify the description of convolution and say it's a superposition of one function replicated at every location of the other function. If we can imagine the other function to be made of large number of delta functions, which does not violate any basic premises, we can have as closely packed set of delta functions following the amplitude of the function that we have at hand at different points. And for each one of them, we can write down a shifted scaled version of the other function. And we take a grand superposition of it. And this is what will give us what the convolution output would be. The important thing to stress here, which is not appreciated, why are we using impulse response as a description of the system. So when we feed a delta function, we know that the delta function has a Fourier transform, which is a flat function, which is constant as a function of the other Fourier coordinate. So whatever might be the response of or description, Fourier description of the device, the impulse is a query amounting to asking an unbiased question, unbiased query. That means we say, tell me your property, and I'm asking this question. It's not a colored question, it's not a leading question. It's a question which ensures that the spectral density is same in the question. That means there's no color to the question. And so whatever response we get can be completely attributed to the system property. And that's why impulse responses have importance that they have. This we'll encounter in variety of ways by different names. It can be an impulse response or a point spread function. We will remind ourselves as and when we encounter those. And all the descriptions so far, although we've been doing it in one dimension, they apply in multiple dimensions as well. Now, using this simple picture, we can even derive the convolution theorem without going through elaborate algebra and calculus. So if we have, let's say, a convolution of f of x with g of x, let g of x be expressed as a sum of scaled and shifted delta functions. And so let's write g of x as sum over some j, where the amplitude of the function at xj is written here. And of course, the delta function has to be located at x is equal to xj. And so this description will give us a delta function based discrete description of gx. So the Fourier transform of gx, which is capital G of s, you can show that using just the shift theorem, where a delta function is shifted by some amount, amounts to a phase gradient, and the scaling still remains because of the linear relationship of the Fourier transforms. And you will find that this is the Fourier transform of g of x. So when we perform the convolution by summing scaled and shifted replicas of f of x, shifted to every location of the component of g of x, you can again do the same trick where you know that the scaling, amplitude scaling is aj. So the scaled version of f of x was used. And so its Fourier transform will be that. And the fact that it was shifted by an amount, you will find it has acquired a phase gradient like this. You can show that this is a sum over j, and f of s is independent of that. So f of s can be taken out, and what will remain is the sum over j of this scale factors times the phase term. And this is nothing but the Fourier transform of the function g of x. And so without going through any elaborate maths, we have proved conceptually that Fourier transform of a convolution is a product of the Fourier transforms. So as we stressed last time, the order in which convolution occurs does not matter, because we can prove that without going through the convolution aspect. We can argue that it's a product in the other domain of the Fourier transforms, respective Fourier transforms. And product has the commutation property, the order does not matter. So here is revisiting the example I had shown earlier now so that we can better appreciate it. So the modulation of a sinusoid by some function f of x can be translated into Fourier domain without doing any elaborate maths by just picturizing the Fourier transform of f of x. If that is something, then it's convolved with a pair of delta functions which describes the Fourier transform of the cosine wave. Depending on the frequency of the cosine wave or the oscillation period of it, you will find the separation between the delta function will vary. As we make this oscillate rapidly, it will amount to more separated delta functions in the Fourier domain. And so you can see the correspondence of these different functions with their corresponding Fourier transforms. When the modulated wave is very slowly varying, very long period, it amounts to bringing the delta functions closer to zero. That means a lower frequency wave compared to the envelope scale. and you will find that these features will merge. But essentially what we're going to use as the way of visualizing convolution is replica of one function at every location of the other function, and scaled by its amplitude. And this description, so if you have a row of houses, you will find identical houses. So you can quickly imagine that to be a set of delta functions at the locations of the houses convolved with the house pattern. You will have, you can quickly arrive at the answer without having to go through a lot of maths. So do play with these things. You will find with more familiarity and more examples, you will feel empowered to visualize the transforms, look at the scales, and take into account the way the scales translate into the other domain in the inverse fashion into account. And you will find very quickly that you can compute or estimate the Fourier transform in the visual way, at least rather quickly than having to go through elaborate maths. This is another example of some signal with a response, which is another function, and you will find that essentially it amounts to putting replicas of this function at every location of this function. We're going to continue this play. Here is an example of, let's say, we want to know what is the Fourier transform of this function, which is a set of delta functions, but limited number of them. So we can imagine that to be an infinite series of delta functions located at the distance of interest and going to from minus infinity to plus infinity. That multiplied by a rectangular window will give us this particular function. So you will find that this function, if it's not set at the origin, will have a Fourier transform of another set of delta functions where the separation between delta functions is inverse of the separation in the other domain. The signs might flip because of the shift from the origin of one of the delta functions. It's symmetric, but it has got integral 0 because of neither of the delta functions is at the origin. And that will amount to basically, you can either visualize it as a shift theorem or compute the Fourier transform elaborately. And you will find that the phase shifts by pi after every separation of delta functions in the other domain. And that's how we see the sign flip alternately. The Fourier transform of this is a sinc function. Remember that separation between the delta functions is much smaller than the width of this function. And so the response of this in the Fourier domain is going to be much narrower than the separation between the delta functions in the other domain. And so the Fourier transform of this function is simply the convolution of these two functions, which is putting the replica of this function at every location of the other function, which is what is done here. You can have this function itself instead of delta function as a set of Gaussians separated by this distance. And if you were to have that, you will find this amounts to a convolution by the Gaussian with this function, which will amount to, in the Fourier domain, multiplication of the Fourier transform of this function with the Fourier transform of the Gaussian. Now remember that the width of the Gaussian is narrower compared to this separation, and so the scale of the Gaussian in the other domain is going to be wider than the separation between these original delta function responses. And so you will find the Fourier transform of convolution as product of these two, and basically this function, which can be expressed as product of set of delta functions going from minus infinity to plus infinity multiplied by a rectangular window convolved with G3. This is what you wanted to explore, and the response of that in the Fourier domain is obtained by simply following the properties at different stages. We encounter this in the context of arrays of antennas in radio. This could also be grating optics and so on and so forth. So we talked about convolution. I had flashed this transparency last time, but I repeated it just to stress the point. that we have seen the correlation integral here, and which has a Fourier transform relating to the so-called Fourier domain modulus square, which in the context of real signals corresponds to power spectrum and the autocorrelation of the signal in the time domain. And people have used this profitably in olden days, where one found it difficult to build spectrometers. So one took the signal from the sky and performed autocorrelation on the signal, measured the autocorrelation function, and later leisurely Fourier transformed it to get the spectrum and to get the spectral information. You can also compute cross-correlation function, which is what we'll be doing routinely in the context of interferometry, where signals received at the locations of the two telescopes or apertures are going to be compared with each other. And when we do that in time, that cross-correlation function can be measured with different shifts to find out similarities with different shifts. And the entire description of cross-correlation function, when Fourier transformed, gives you what is called a cross spectrum. And the hope is that the similarity measure will come out as a component which is amounting to the autocorrelation function here. That means the similar components, the things that are similar to F and G, will stand out as the power spectrum contribution. So this is what I said, and we will be using this as a tool for measuring the spatial coherence, mutual coherence function in interferometry. Here the order matters, what you correlate with what, but you can see that, it's a flip of axis that you need to take into account when it's like A correlated with B versus B correlated with A. You will find the phase relation apparent from it will change sign, and that as long as you take that into account, you're okay. Given the case of our imaging of the sky, where the brightness distribution is real, you will find the visibility itself has the property of Hermitian symmetry. And so if you measure it with a pair A and B of apertures, you will find that the measurement the other way, where B is correlated with A instead of A with B, will be related to each other by a simple complex conjugate. So many times, more often than not, measurements are made only with that pair, and the information about the diametrically opposite component in the UV domain, in the spatial frequency domain, is assumed to be also measured, where the value of what you measured on one side is put with the complex conjugation and used routinely. This is just to drive home the point. In the other context, I just mentioned one pair where the correlation, autocorrelation corresponds to power spectrum in the Fourier domain when it's a time and frequency pair. Even in the aperture domain, which is the other two of the three dimensions we will be dealing with, we will find that a square aperture, John has already shown you that for a rectangular aperture, the beam, the response pattern will be a product of two sinc functions in the two orthogonal directions. And so it's a 2D sinc. You will find that, take the power pattern, you will find that you will be squaring it, and that will be a sinc square function in 2D. You can ask what happened to the effective aperture distribution corresponding to the power pattern. And you can see that that is an autocorrelation function of this square aperture window. And in each dimension, you can visualize how the rectangular window turned into a triangular function, autocorrelated or self-convolved. And you can visualize that this will turn into a pyramidal function with a rectangular, with a square base. That's what you will be finding, that when you have an aperture of certain width, let's say D, you will be measuring spatial frequency component to the extent of plus minus D on either side of the zero by a single aperture thing. And the same similar spread will continue when you also do the cross correlation. You must have encountered correlation in variety of contexts. Most familiar context is the linear regression, where we trying to look for linear trends in two sets of data or two parameters, where we plot one against the other and look for any relationship between them. More often than not, we look for linear relation either on the normal scale or in log-log scale, in which case it's a power law description. But essentially what we do there is what we try to do in the formal cross-correlation computation. Formally, the cross-correlation function can be defined as the function minus its mean value, because we don't want the mean values to just give a product and give some pedestal correlation. So what we want to see is the fluctuation or the deviation of the function from its mean, how they are related to similar deviations or deviations in the other function at the corresponding points, or at a shifted version of those corresponding points. So you will find that x0 is a variable. It's the lag or the relative shift that we wish to explore to see how the correlation behaves as a function of this shift. And if you want to make it independent of arbitrary scales in f and g, you can often divide that by the square root of the product of variances in this two, which are again measures of the fluctuations about the mean. So this is the standard definition of cross correlation, which you can find in any number of books, and the normalization given like this. So when we measure the visibilities and so on, this is what we are actually trying to measure. I mentioned that the natural process of physical devices is to convolve. You can have, and I said with some trick, you can get this to perform correlation. Naturally, there's no physical system which performs correlation. So you will find that you have to do that operation explicitly, and the way to achieve that is to give a conjugate characteristics to the device, so that when convolution occurs with the conjugate function, you will get effectively autocorrelation function. And this is called match filtering. This word would have appeared purely as electrical engineering term for a long time in past. Thanks to the LIGO context and the gravitational wave detection context, that people have now been using this term more routinely in astronomy. You can show that this is what we do for optimum detection. The optimum detection amounts to match filtering. And effectively, what is it? We are, this is like having a set of keys, and we want to find the matching key with the one that we have. So instead of comparing overlapping keys with each other and seeing the similarity, the easiest way is to make a lock that opens with the key of our interest, and see which one of the keys opens that. And so the conjugate filtering is exactly that, nothing less, nothing more. So what we make is a lock, which is the device, which can be achieved in software as well as in hardware. So this is routinely used in pattern recognition, pattern matching. You will find that you can use this everywhere practically where there is the presence of random white noise is assured. If there is a colored noise, then there are confusions that can arise from the color of the noise, and you need to take into account, in which case some other strategy, slightly modified strategies to be employed. But let me stress that traditionally what is being done as a square law detection, where we get simple signal voltages, and traditionally people used to put even a diode detector in a square law regime to measure the intensity accurately, is also a match filtering operation, where the modulus squaring amounts to actually multiplying a signal of unknown description. In the absence of the signal description, you cannot build a device. So you use the same function and use its conjugate description, and use that as a convolution convolver, and which is what amounts to modulus squaring. You can show, if anybody is interested, that you could have taken the signal voltage and taken instead of modulus squaring it, you could have taken the fourth power of it, fourth power of the modulus. And then you can do the integration and so on, and then recover quantity of interest, which is intensity, by square rooting the result you have after having taken the fourth power of the modulus and integrated. You will find that the contrast of that measurement is poorer than what you would get in the square law detection. There are various examples. People routinely use Nash filtering in one form or other, whether they admit it explicitly or not. That's the only way you're going to get an optimum detection in the presence of noise. I'm almost at the end of it. I will probably take this up tomorrow in the next lecture. Okay. The issue of coherence and correlation is often confused. Although they are related, there is certain clarity required in the way we understand coherence, which I would like to elaborate on in the next lecture. Thank you.